Okay. I'm Sam from China. The title of my presentation is Hacking Windows CE. It's about the security problems of the PDAs and the mobiles. My presentation is constructed with 8 parts. First of all, I'll make a brief introduction of Windows CE because ARM processors is the most useful processor in PDAs and mobiles. So I'll introduce the ARM processors architecture. You know, understanding memory management is very important for buffer overflow. And the second, I'll introduce the memory management with graphs. Compared with other Windows systems, Windows CE treats processes in a different way. Then I'll introduce the features of processes and the threads of Windows CE. The Windows CE API search address search technology is funny. I'll introduce it to how to write shellcode use this method, and I will also introduce the implementation of system call and use it to write shellcode. After this, I'll demonstrate a simple buffer overflow. Well, I think this technology will be improved in the future. Then I'll talk something about decoding shellcode. The decoding shellcode will make the real shellcode more universal, but ARM processors cache architecture makes it funny. At last, I'll conclude my presentation. Okay, let's move on to the next part, the first part. Windows CE is a very popular embedded operating system for PDAs and mobiles. The name is developed by Microsoft. Because of the familiar APIs, Windows developers can easily develop applications for Windows CE. Maybe this is a very important reason that makes Windows CE popular. Windows CE 5 is the latest version, but Windows CE.NET is the most useful version, and my presentation is based on this version. Maybe for marketing reason, there is a Windows mobile software for Pocket PC and the smartphone in Microsoft's website and MSDN, but they all based on the core of Windows CE. By default, Windows CE is in little endian mode and it supports several processors. Almost all of the embedded devices will use ARM as CPU. ARM processor is a typical RISC processor, which implement a load-store architecture. Only load and store instructions can access memory. The data operating instructions operate on register contents only. There are 6 major versions of ARM architecture. The demonstrated device has a Samsung S3C2410 processor, which has a ARM9 core, and the architecture version is ARMv4T. More and more PDAs are using Intel Xscale processor, which architecture version is V5TE. ARM processors support 7 processor modes depending on the architecture version. These modes are user, FIQ, IRQ, supervisor, undefined, abort, and system. The system mode requires ARM architecture v4 and above. All modes except user mode are referred to privileged mode. Applications usually running user mode, but on the Pocket PC, all applications running in kernel mode. Well, I'll talk it later. Windows ARM processor has 39 registers. These registers are arranged in partially overlapping banks. There's different register bank for each processor mode. The bank registers give rapid context switching for dealing with processor exception and privileged operations. In ARM architecture v3 and above, there are 30 general purpose registers, the program counter register, the current program status register, and the 5 saved program status register. 15 general purpose registers are visible at any one time, depending on the processor mode. By convention, R13 is used as a stack point in ARM assembly language. The C and the C++ compilers always use R13 as the stack point. In user mode and system mode, R14 is used as a link register, which stores the return address while a subrouting call is made. The program count register is accessed as R15. It can access directly by data processing instructions. This feature is different from other processors, and it is useful for code location while writing shell code. Understanding memory management is very important for buffer overflow. But compared with other Windows systems, Windows CE chooses memory management in different way. Windows CE uses ROM and RAM. The ROM in the Windows CE system is just like a small read-only hard disk. It stores the entire operating system as well as the applications that are bundled in the system. The data can maintain inside the ROM without power or battery. The RAM in a Windows CE system is divided into 2 areas, the program memory and the object store. The object store can be considered something like a permanent virtual RAM disk. It's unlike a RAM disk in the PC. It can maintain the files in it even if the system turned off. That is the reason that this is the reason that Windows CE devices typically have a main battery and a backup battery. They provide the power to the RAM to maintain the files stored in it. Even when the user hits the reset button, the Windows CE kernel starts up looking for previously created object store. The system will use that store if it finds one. Another area of Windows CE RAM is program memory. Program memory is just like the RAM in the PC. It stores the heaps and the stacks that the applications that are running. The dividing of between the object store and the program memory is adjustable. The user can move the dividing line by the system control panel applet. Windows CE is a 32-bit operating system, so it supports 4 GB virtual address space. Let's look at this graph. This is the 4 GB virtual address space layout. The upper 2 GB is is a kernel space used by a system for its own data, and the lower 2 GB is user space. From this address to below this address, memories are used to large memory allocation, such it's used by such as memory mapped files. Object store is loaded here, and from 0 to below, these memories are divided into 33 slots, each of which is 32 MB. The slot 1 is the XIP, execute in place. This is a new feature of the Windows CE.NET. It expanded the application's virtual address space from 32 MB to 64 MB. Well, this graph is the slot 0 virtual address space layout. Slot 0 is very important. It's used by the current active process. The first 64 KB is reserved by the OS, and the following is the processes code and data. Stacks and heaps are arranged here. DL files are loaded into the top address. Well, let's move on to the next part. Compared with other systems, Windows CE treats processes in a different way. Windows CE limits 32 processes being run at any one time. When the system starts, at least 4 processes are created. Let's look at the previous graph. NKEXE, which provides the kernel service, it's always loaded into the slot 97. Filesys.exe, which provides the file system service, is always in slot 2. Device.exe, which load and maintains the device drivers for system, it's in slot 3 normally. And GWES.exe, which provides GUI support. The other processes are also created, such as Explorer. The threads on the Windows CE is similar to threads on the other Windows system. Each process at least has a primary thread associated upon starting, if it never created one. One process can create any number of threads, only limited by the available memory. Each thread belongs to a particular process and shares the same memory, but the set permissions API can give the current thread access any process. Each thread has an ID, a private stack, and a set of registers. When the process is loaded, the system will assign the next available slot to it, and their files loaded into the top address of the address space, and then followed by the stack and default process heap. After this, then executed. When the process thread is scheduled, the system will copy from its slot to slot 0. It's not a real copy operation. It's just mapped into the slot 0. This is mapped back to the original slot allocated to the process if the process becomes inactive. Process allocate stack for each thread. The default size is 64 KB, depending on the link parameter when the program is compiled. This size can be modified. The top 2 KB is used to guard against the stack overflow. We can't destroy this memory, otherwise the device will freeze. And the remainder available for use. Variables declared inside the function are allocated in the stack. Thread stack memory is reclaimed when it terminates. Well, let's move on to the next part. Before exploit, we must have the shellcode to run on the Windows CE. Windows CE implements Win32 compatibility. The core DLL provides the entry points for almost all the APIs that implement that in the core DLL. We must search the necessary API addresses and then use these APIs to implement our shellcode. The traditional method to implement the shellcode in the other Windows system is to locate the kernel 32 or NTDLL via PEB structure, and then search necessary APIs via phead structure. Well, is there any structure like PEB on the Windows CE? The answer is yes. That's the kernel, the kdata structure will satisfy us. It's defined in nkarm.h. Kdata structure is a very important kernel structure. Can be accessed from user mode by fixed address p user kdata. The value over p user kdata is defined in the kfuncs. It's in the normal SDK. The value, the p user kdata is FFFC800 in ARM processors and 5800 on the other CPUs. Well, let's look at the last member of kdata structure. It's offset 300 from the start of kdata structure. There is the AIN4 is a D-word array, and there is a point to the module list in index 9. So offset 324 from the FFFC800 is the point to the module list. Well, let's look at the module structure. It's defined in kernel header file. The second member is P mode. It's a point to the next module of the module chain. The third member is LPSZ mode name. It's the module name string. So we can locate the core DLL via comparing the Unicode string of its name. Well, we also notice the E32 member. Let's look at this file. E32 member is a E32 lit structure. It's defined in PEHDR. Well, let's look into the E32 lit structure. The E32 vBase will tell us the virtual base address of the module. So we can locate the virtual base address of the core DLL. We also notice the last member is E32 unit. It's an info structure, and the info structure has two members. The first is the virtual relative address, and the second is the size. And the lit extra is defined in the PEHDR, the start of PEHDR. Six members used by NK, and the first is the export table position. So from now on, we got the virtual base address of the core DLL and its export table, the relative address of of the export table position. I wrote a small program to list all the virtual base address of all loaded DLL files. This is the KData structure, and offset 324 is the point to the module structure, and the module structure is the chain structure. The offset 4 will point to the next module. Well, the point to the module structure is in the kernel space. So this program only executes in the kernel mode. The user mode, it will fail in the user mode. The most of Pocket PC ROMs were built with the full kernel mode option. That the applications appear all running kernel mode. So this small program will execute in the most of the Pocket PC. I use this program to get the virtual base address of the core DLL is 1F60000. But when I use EVC debug to look into this address is invalid. The valid data is from 1F61000. I think maybe the Windows C is just for the purpose of save memory and start time, and then didn't load the head of the DL file. Okay, the WinCE 4.dust uses ordinals to find the API address, but I think use API name to find the API address is more reliable for shellcode, because the API name won't change even if the CoreDL file is changed. We can because we have the export table position and the base address of the CoreDL, so we can compare the image export directory to find the API address via API name. To save size, we can use the hash technology that from the LSD's Win32 assembly components. And this graph is ripped from LSD's Win32 assembly components too, and it shows the way to locate the base address via API name. Well, let's move on next part. The test ASM is our final shellcode. It constructs with 3 parts. First, it will call get export section to get the virtual base address of the CoreDL and its relative virtual address over export table position, and then it uses find function to find the API address via the hash value of the API name, and then store the API address to the its own hash value position. The last part is our the implementation of our shellcode. It will change the register key over Bluetooth, and then use kernel I/O control to soft restart it. This shellcode will open the Bluetooth over some IPEX. We must notice the some ARM assembly LDR pseudo instruction. Look here, why I comment of these instructions. Because this pseudo instruction will be this in the EVC debug. It depends on the program, so it won't get the FFFC800 in the shellcode. So this instruction will make the shellcode fail. and the next instruction will be this in the EVC debug. It's okay. Well, in Windows CE, the R3 and the R0 and to R3 used the first to fourth parameters of the API. If the parameter is larger than 4, the other parameters will stored in the stack. So we must pay attention while writing shellcode because the shellcode always in the stack memories. Well, EVC debugger has some bugs that make debug difficult. The first, EVC will change the stack contents when the stack reclaimed in the end of the function. Well, it's difficult to debug the buffer overflow because the shellcode may be changed. And the instruction of the breakpoint may be changed to E600010 in EVC sometimes. Well, it's very bothering. And EVC allows the code modify the text segment without error while using breakpoint or when you step by step to debug into. But sometimes it's useful. Well, the 8 Pro for the ARM debugger also have these bugs. So I think maybe this is a bug of the debug API over Windows CE. Maybe. Well, let's move on to the next part. The above shellcode we talked is complicated and it can't run in user mode. Is there any other method to implement shellcode? Well, let's look at an API implemented in the core DLL. Well, let's look at the power off system. It has no parameters. The first, the system will check the K-thread info structure. And the K-thread info is initialized in the MD created thread 2 function in the MD arm.c. If the application running kernel mode, this value will the K thread info will be set with 1. Otherwise, this value is saved 0. Yeah. So it tests this memory is 1 because the if K thread info is 1, then the system will use the API set table to find the real implementation in the kernel space. If your application is running kernel mode, and this instruction will execute. The R1 is start from the 8 blah blah blah. It's in the kernel space. Otherwise, if the k thread info is zero, the system will use this. This is the system call over Windows CE. The system call number is from F0000 to F001000. There is a formula to determine the API, determine the system call number. It's like this. So, use this formula, we can calculate the system call number. Well, let's calculate the kernel I/O control. Kernel I/O control is in the defined in the kwin32.c, and the API set is 0, and the index is 99. So we calculated the system call number is like this, F000 FE 714. Well, the system call number is more stable than the API address that implemented in the core DLL, because the variable compiled ROM, the API address is a variable. So this shellcode is very simple. It only uses the system call to So this shellcode will can execute in the user mode, but also the kernel mode. So I think this shellcode will used in the smartphone. The smartphones run not built with the full kernel mode option, and Microsoft device emulators run has no this option too. I tested this shellcode success in the Microsoft device emulator and my demonstrated device. Okay, let's move on to the next part. The hello CPP is my demonstrate vulnerable program. It reads the bin file of the root directory by fread, and then read the file to the stack variable buff, and the buffer is only 512 bytes. So if the bin file is larger than 512 bytes, the program will overflow. And the printf and the get chart is just for test. They have no effect without the console DLL in Windows directory. The console DLL can obtain from Windows Mobile Developer Power Tool or from the Pocket Console. Windows CE uses BL to call a function, and in the hello function, this is the first instruction. The store AOR to SP. It will store the AOR rest to the stack stack, which contains the hello caller's address, and the AOD-MIR SP to PC is the latest instruction in the hello function. This instruction will load the AOR rest that is stored in the stack to the PC register, and then the program will flow to the winMain function. Then it will return. So, overflow the AOR rest that stored in the stack. We will obtain the control while the function returned. The variable's memory address that allocated by the program is corresponding to the loaded slot, both stack and heap. The process may be loaded into the different slot each start time. So the base address of the slot always alters. But we know that the slot 0 is mapped from the current process slot, so its stack address is stable. Anyway, you can use an jumper instruction address to let the program flow to your shellcode. Well, I tried two methods to construct the exploit buff. The first is like this. The start is the pad instructions, and then is the return address that we overflow it, and this return address is pointed to our shellcode. Well. This exploit buff is larger. The PDA is frozen when the hello program is executed. I think maybe there are two reasons. The first is that the stack of Windows CE is small, and maybe the buffer overflow destroyed the 2 KB guard on the top of the stack boundary. So I changed it to another method to construct the exploit buff. It's like this. I move the shellcode in the start position, and then the last is the return address that point to our shellcode. Well, I use this method success. I'll demonstrate it. Okay. The first, the Bluetooth is closed, and I'll execute hello. It will print the address of the buff and the size. When I press any key, the device is restarting. Well, it has restarted. Well, after the system restart, the Bluetooth is opened. Well, I'll close it because it's danger. Okay, let's talk something about the decoding shellcode. The above shellcode that we talked is a concept shellcode. It contains a lot of zero. Well, the other vulnerable programs maybe filter the special characters before the string buffer overflow in some situations. For example, overflowed by str copy. It's difficult and inconvenient to write a shellcode without special characters, because if you use the R0, the OP code will contain the zero. So we think about the decoding shellcode. The newer ARM processor has a Harvard architecture, which separates instruction cache and data cache. This feature will improve the performance of the ARM processor, but the self-modifying code is not easy to implement because it will affected by the ARM cache architecture and the processor's implementation. Oh. Well, let's look at this shellcode. Well, this is the decoding shellcode for the test. The last four instruction is move the 1 to the R1 to R4 registers, and the beginning of the first four instructions will modify the last instructions. It will make the value to 99 because the R1 is 99. So the R1 and the two R4 registers will get the 99 in my demonstrated device. Well, we can saw the last 4 instructions has modified. But it will need more NOP instructions between the decoded shellcode and the real shellcode in the Intel X scale processors. You can try it. Maybe only the R1 get the 99. I think maybe the ARMv5 architecture has 6 pipelines, and my demonstrate device only has is ARMv4. It has 5 pipelines. Maybe the pipelines modify will affect the result. Well, let's look at another method. Well, in this method, the last 4 move instructions were encoded with the exclusive OR with the 88, and the start is the decoding shellcode. It has a loop to load the encoded shellcode, to load 1 byte of encoded shellcode, and then decode it, then stored it to the original position. Well, the R1 to R4 registers won't get the 1, even if you add a lot of the NOP instructions. Well, we saw the last 4 instructions is decoded, but they don't get the 1. So I think maybe the load instructions will trigger the cache, some feature of cache architecture. So we must need to flush the iCache or dcache after the shellcode decode. Well, I think the first I think about the system interrupt. I use the system interrupt success in the AX PowerPC and the Solaris Spark, but the SWI instructions in the Windows C is just nonsense. The SWI handle defined in the ARM trappers, it's just move the AOR rest to the PC, so it's just a NOP instruction. Well, I have to try another method, because the Pocket PC ROMs were built with the full kernel mode option, the applications running the kernel mode. So I think about the MCR instructions to flush the iCache and dcache. the MCR instruction can access in the kernel mode only, but unfortunately this method all failed. Okay, let's move on to the last part. The codes we talked about are the real-life buffer overflow example in Windows CE. It's simple, but I think this technology will be improved in the future. Because the instruction cache and the decoding shellcode is not good enough. Well, the internet and the handset devices are growing quickly. The threats to PDAs and the mobiles becomes more and more serious. The patch over Windows CE is more difficult and dangerous because the entire operating system is in the ROM, contained in the ROM, and if you want to patch the system floor completely, you must flush the system. You must flush the system. You must flush the ROM, and it is danger and it is danger and difficult for the normal customers. Well, I consulted a lot of paper on the internet. It's all listed here. I'll show my special appreciation to Nasri, who helped me a lot. Well, that's the end of my presentation. Hope you enjoyed, and sorry my lame English. Thank you.